Hi, this is Professor Fernandez, and in this video, we are going to work out an example of calculating, Taylor polynomials. I'll fix that. So the example comes from the notes from lesson 13 in this Calculus 2 course. You can find those notes on this website, along with these other resources. So in video 13.1, right, this is video 13.2, I reviewed what Maclaurin polynomials are. And I talked a little bit about how the fact that they're polynomials leads you to wonder, what's so special about them? What makes them Maclaurin polynomials? Long story short, it was all about the coefficients of the polynomial. I'm going to zoom in down here. This is the next definition in these lesson 13 notes, which again you can get on that website. And just remind you what a Taylor polynomial is and how it's different slightly from a Maclaurin polynomial. First of all, same assumption kind of as the Taylor polynomial, that the function is differentiable n times whatever n happens to be. If you're looking for a third degree Taylor polynomial, 19th degree, n here is a quote whole number. However, not at 0. It's differentiable n times at x equals c. So c here could be a number that's different from 0. So when c is equal to 0, we talk about Maclaurin polynomials. When c is different from 0, we talk about Taylor polynomials. The nth degree polynomial then, t sub n of x, slightly different notation. Last time we used m sub n for Maclaurin, here t for Taylor, equals blah, is called the nth Taylor polynomial of f at c. Just if you either go back to the previous video or if you kind of remember what the Maclaurin polynomial looks like, the only difference here with this polynomial, there are two really. First of all, everywhere there used to be a 0, there's now a c. This used to be f of 0, this used to be f prime of 0, this used to be f double prime of 0. Now they're all replaced by c's. Because we're no longer restricting ourselves to looking just at x equals 0. We could be looking at x equals c where c is different than 0. Second difference, in the Maclaurin polynomial, I'll just write it out here since we keep talking about it and comparing it. This was the Maclaurin polynomial, m sub n of x, right? Because you're looking at x equals 0, this is a power, this is a power series centered about 0, right? So in sigma notation, this was kth degree derivative at 0 over k factorial, x to the k. And really, this is x minus 0 to the k, right? In the Taylor polynomial, right, again, everything is centered around c. So you get a power series centered at c. So you get all these powers of x minus c everywhere. Okay, so that is a quick little review of what a Taylor polynomial is and how it relates. And it's a little different from the Maclaurin polynomial. So now the point of this video is to show you how to calculate that for a specific function. Let's take ln of x and let's take c equals 1. Again, you can pick whatever c value you want and try to calculate the Taylor polynomial. You are going to have to, remember the assumption, substitute these into the derivatives of the function. So the function has to be differentiable at up to order n at x equals c. So there is that requirement. And we'll check that right now. Right? So the function here, f of x, is ln of x. So let's start calculating some derivatives. The first derivative is 1 over x. The second derivative, to do that, we're going to write the 1 over x as x to the minus 1. Second derivative is negative x to the negative 2. I'm going to leave it that way, and you'll see why in a minute. I'm not going to convert it to a fraction. Third derivative is now I bring down the negative 2, and this is negative 1 times negative 2 x to the minus 3. I'm going to leave it that way again. I'm not going to simplify it. And that's because, we're trying to find a pattern here so that we can write down the nth term, where n is whatever whole number you want, in the Taylor polynomial. What I am going to do is help myself out by trying to figure out if there are any patterns I spot right away. First of all, notice that I have a negative 1 times a negative 2. So I have two negative 1s times a 2 times an x to the minus 3. Okay? So already the way I've written hopefully suggests that you might be able to figure out what the next derivative is by just following the pattern. So this is 2x to the minus 3. If I differentiate that, I bring down the 2, and now it's negative 3 times 2. Sorry, I bring down the minus 3. Negative 3 times 2, x to the minus 4. Okay, so this is now, it adds another -1. So I had 2 -1s, now I have 3 -1s. And then I have a 3 times a 2. Hey, that's 3 factorial. And then I have x to the -4. At this point, we have enough of a pattern that I think we can predict the next term. So let's do that. Let's predict and then verify. So we predict that the fifth derivative evaluated, of the function really, is going to be, well, let's look at the pattern here. This was a 4, so this was a -4, so we think it's x to the -5. And this was a 4, and here was a 3, here was a 3, 1 less. So maybe -1 to the 4th times 4 factorial. That's our prediction. So let's verify. This here is -6 x to the -4. Let's find the derivative. That's going to be bring down the -4, so -6 times -4 x to the -5. Okay, and -6 is, well, first of all, there's a negative times a negative. That's positive. So this is 6 times 4. And 6 is 3 times 2, and here we have a times 4. Sure enough, 4 times 3 times 2, that's 4 factorial, x to the -5. And it's positive. And over here, we predicted -1 to the 4th. That's positive. So we got our prediction, and I think we can pretty confidently say now that we have found the pattern for the derivatives of x, of ln of x. Okay, so then what is the pattern? So now we can jump to the nth derivative of x. We follow the pattern. This number matches the power of x, so x to the -n. And then we have a -1 raised to the n-1, right? 1 less than the power. And then the factorial here is also 1 less, so n-1 factorial. So this is the nth derivative of the function, right? And this is what we are now going to use to substitute in the c value and then start generating the coefficients in the Taylor polynomial. So let's do that over here. Draw a line here. And we can also do it from the work we've already done here. We're looking for the Taylor polynomial at c equals 1. So let's use this information that we already wrote down. Why not? So f of 1 is ln of 1. That's 0. F prime of 1 is 1 over x evaluated at 1. So that's 1 over 1. That's 1. F double prime of x is -1 over x squared evaluated at 1. So -1 to the -2. That's -1. And then third derivative, oops, I should have put 1 here. Third derivative evaluated at 1. So here's where we get, I'm looking over here. Here's where we get a 2, right? And then a fourth derivative evaluated at 1. I'm looking over here. We get a -3 times 2, -3 factorial. Okay, so now we have enough information that we can go back along with this, which is going to help us out with the nth term, and start writing out the Taylor polynomial. So let's do that. So t sub n of x equals, we'll just write out the general form to remind ourselves here of what that is. There we go, x minus c squared, and then plus all the way up to nth derivative evaluated at c over n factorial x minus c to the n. And now we just start putting things in, right? So f of 1 was 0, so that's 0, plus f prime of 1, so that's 1, times x minus the c value. C is 1, so x minus 1. Okay, plus f double prime, that's a -1 over 2 factorial, x minus 1 squared. And then I'm gonna write out a few more terms because you'll see that something's gonna happen, some cancellations. F triple prime of 1 is 2. So that's 2 over 3 factorial, that's the next term, x minus 1 to the third. And then keep going here. Fourth derivative at 1 is -3 factorial over 4 factorial, x minus 1 to the fourth. And then it keeps going until it gets to our nth derivative term. Here it is, right? So -1 to the n minus 1, -1 to the n minus 1 times n minus 1 factorial. And this is the nth derivative evaluated at x, right? If we now substitute in x equals 1, then this part goes away, and we're just left with this term. So this is the numerator that I've written over here on the right hand side. That gets divided by n plus by n factorial, right? Because the derivative order of the function matches the power of x minus c, right? I'll zoom in here to remind you of that. See, this is n, that's also n. And by the way, of course, that's also n factorial down there. Okay, so it's this times x minus 1 to the n. All right, now we get to step back and see if we can, we'll simplify first and then see if we can spot any patterns here. The 0 doesn't do anything, so I start off with x minus 1. Then over here, it's a negative x minus 1 squared over 2 factorial. And then next one here, here's where we can start seeing some potential for simplification. Remember that 3 factorial is 3 times 2 factorial. And we have a 2 up here. Remember that 2 factorial is 2 times 1, so it's just 2. Okay, so this 2 then cancels with that one. So what I'm left with is a positive x minus 1 cubed over 3. Not 3 factorial, right? 3. And then next term, which is this one. So let's take a look at what we can do there. So because of the negative sign, minus 3 factorial over 4 factorial, x minus 1 to the 4th. We're going to play the same game here. 4 factorial is 4 times 3 factorial, and look, this 3 factorial cancels with that one. So actually, I can just write the numerator, simplify it down to 1, and remove the factorial from the denominator. And notice what I just said. If you rewind it, that's the pattern. So the next term, it seems like it's alternating, right? Plus, minus, plus, minus. Next term is going to be a plus. I'm going to put a 1 in the numerator. This would have been 5 factorial, x minus 1 to the 5th, but like we just said a minute ago, we remove the factorial from the denominator. Okay, and that is the pattern, that ln of 1, ln of x. Its Taylor polynomial at c equals 1 follows. And then if we keep going here, plus, dot, 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 plus, what's the last term over here on the right-hand side? Same thing. The denominator, n factorial, is n factorial, n times n minus 1 factorial. And that n minus 1 factorial cancels with the numerator. So the last term down here is minus 1 to the n minus 1 over n times x minus 1 to the n. Okay, so now let me erase everything so we have enough space to actually write down the final answer. So we finally get that the Taylor polynomial at c equals 1 for ln of x is x minus 1 minus x minus 1 squared over 2. Notice that there is a 2 factorial down there, but 2 factorial is 2. So I'm now going to start following the pattern of the rest of the terms. And the pattern is, number 1, they alternate. And number 2, the denominator is not a factorial. The denominator is just the same as the power of x, right? No factorial, over n x minus 1 to the n. That is my Taylor polynomial. What if we wanted to write this now in sigma notation? Well, so everything has an x minus 1, and they're all powers of x minus 1. And the first term is 1, right? X minus 1 to the first. There is no x minus 1 to the 0. There is no 1 plus x minus 1, right? So we know that k starts at 1. It's going to go all the way to n. We can just leave it that way. And then what is the general term? Well, there's an alternation, and we've already figured out that it's this type of alternation. Minus 1 to the k minus 1. Okay, and then we also figured out that the denominator matches the power of x, so divided by n. Okay, so I'll put this all in the same color. There we go. And this is therefore the sigma notation, closed form, of the, and I should do one thing. Instead of making it n down there, let's make it k, so we don't intermix the variables and the dummy variable here and the upper limit of summation. So that is the term by term written out Taylor polynomial at c equals 1. This is the sigma notation written out version. And that's it for this video. Thanks for watching.